Okay, so here's what we're looking at. So we mostly talked about this in the lab when we did our synapse activity, but let me just review this for you for our exam purposes for lecture. We have a presynaptic neuron here. We have our synapse, where we have the release of the neurotransmitter, which will diffuse across that synaptic cleft and bind to a receptor located on the membrane of the postsynaptic neuron. Okay, so that's our structure here. I'm saying, okay, we're going to talk about this first one, that neurotransmitter that's been released is excitatory. So if it's an excitatory neurotransmitter, when it binds, it's going to ultimately open a sodium ion channel. So sodium ion channels are associated with excitatory neurotransmitters. When that sodium ion channel opens, sodium will move down its concentration gradient, moving from high concentration outside the neuron to low concentration inside. It's carrying a positive charge with it. So the polarizing event that will occur is a depolarization. So remember that here's our situation at rest. The resting membrane potential is -70. So if you cause an influx of cations, that's going to raise that polarity to a less negative value, right? It's either going to be less negative or more positive, whichever way you want to think about it, but that is a depolarization. So again, excitatory neurotransmitters cause a depolarization. If that depolarization, once it reaches the hillock, if it has met the threshold value, which is typically -55 millivolts, then an action potential will be generated, right? So again, if the depolarization created by the influx of sodium meets the threshold value once we're at the axon hillock, then we will generate an action potential along the axon. So remember that potentials that occur here on the cell body and dendrites are graded potentials, and the potential that will occur here or signal that will be created on the axon is an action potential. Action potentials are generated if we've met the threshold value. Okay, so that is an excitatory neurotransmitter. Now let's look at this pathway here, where again we have a presynaptic neuron, our synapse, and our postsynaptic neuron. Now we're saying we have an inhibitory neurotransmitter. So the presynaptic neuron is releasing an inhibitory neurotransmitter, which diffuses across the synaptic cleft, binds to a receptor at the cell body of our postsynaptic neuron here. We have two different options here. If it's inhibitory, it might open a chloride ion channel at the membrane of the cell body of our postsynaptic neuron. So if it opens the chloride ion channel, chloride ions are in higher concentration outside the cell than they are inside the cell. So chloride will move again down its concentration gradient, simple diffusion, moving into our cell body. Chloride ions carry a negative charge, right? So if we have all these negatively charged ions coming in, that's going to create a polarizing event that's going to be called a hyperpolarization. And so that's what you're seeing here, what I've drawn here. It makes it more negative on the inside. If it's more negative, it's a hyperpolarization. So we go from, again, our resting membrane potential at -70 to an even more negative value. Well, that's going to take us away from the threshold value, right, which is -55. So it's taking us further away from threshold. So that's going to prevent an action potential from being formed. So when we reach the axon hillock, the hillock says, no, we're nowhere near threshold, so we will not generate an action potential. And that is why, it's considered an inhibitory neurotransmitter. So that's one option. One option is for that neurotransmitter to open the chloride ion channel. It could also open a potassium ion channel. So it's actually either or perhaps both. So at any rate, if we open the potassium ion channel, remember that potassium is high inside the cell and low outside the cell. So potassium will move down its concentration gradient, moving from high to low concentration. when it does so, it's carrying positive charges with it. So it's removing positive charges from the inside of that cell, which is going to give us the same kind of response. It's going to make it more negative on the inside. So opening a potassium ion channel here at the cell body, again, it's going to create a hyperpolarization, which will inhibit or prevent the formation of an action potential. Okay, good. So at any rate, that just kind of summarizes what we've looked at. I do want to remind you really quickly of something else, couple things. So these ion channels I talked about opening, all three of these, they would be considered ligand-gated ion channels, right? Or chemically gated ion channels, because they're responding to a chemical. They're responding to the neurotransmitter. So they're ligand-gated or chemically gated. The ion channels involved in generating the action potential are going to be voltage gated. They're voltage gated because they're responding to that change in voltage. They're responding to that, in this case, it's depolarization. Great. Now, one more thing. It's not on your lecture exam, but it will be on your lab exam. Recall that we have different kinds of receptors that neurotransmitters bind to. They're either ionotropic or metabotropic. And so we went through that in some detail in the lab with that synapse activity. I just want to remind you that there are, differences between the receptors. Okay, so I hope that helps put some of these concepts together. All right, let me know if you have any questions.